Hi, my name is Timo Völker, and together with Michael Tüxen and Erwin Radke, I wrote a paper about the search of the PMTU with QUIC. In my presentation about the paper, I start with the introduction about the PMTU discovery. Then I talk about the PMTU discovery framework in QUIC. Then I focus on the PMTU search, show how we evaluated our search algorithm, and I conclude our work. Okay, let's start with the introduction. The MTU stands for the maximum transmission unit, and what I mean with MTU is the IP packet size limit for a link. If we consider two endpoints connected via two routers, we have three links. Each link can have its own MTU, which I named M1, M2, and M3. With PMTU, the PMTU is the IP packet size limit for the whole path, which is in fact the lowest of all link MTUs, or in this example, the minimum of M1, M2, and M3. So why should we care about the PMTU? Well, we could limit the size of all of our outgoing packets only by the local link MTU M1, as shown in this example, and let routers that can't forward this packet size fragment the packet and forward the IP fragments. However, this is possible, but only for IPv4, because with IPv6, only the sender is allowed to fragment packets. And moreover, this is IP fragmentation is considered harmful, as Christopher Kent and Jeffrey Morgan wrote in their paper. What else can we do? We can send IP packets that are small enough to avoid any size constraints. As shown in this example, the router don't have any trouble to forward small packets. But this requires to send more packets, and as each packet contains its own headers, it increases the overhead. And as each packet needs to be processed by the sender, the routers, and the receiver, we consume more processing power, which reduces the throughput, as Kazuo Uko and Jana Inga showed for QUIC in a blog post from last year. So we should care about the PMTU. How can we discover the PMTU? The classic way is to initially limit the size of outgoing packets by the link local MTU, M1, and to set the don't fragment bit in all outgoing packets, which is implicit for IPv6 packets. This triggers the router that would fragment the packet to drop the packet instead, and to respond with the packet-to-big message reporting the MTU of the following link. And with this information, the sender can reduce the size of its outgoing packets such that the router can forward the packet. This might continue repeat with another router on the path to the destination, but eventually we will find the PMTU. But in the current internet, a sender can't rely on receiving a PTB, because routers exist that, for example, silently drop packets that are too large. And this results in a black hole situation where the sender keeps sending packets that are too large, which are dropped silently by the router. So if we can't rely on a signal from the network, we shouldn't depend on it. And as IP needs some form of a signal, we should instead implement the PMTU discovery in an acknowledged packetization layer protocol. The IETF recently standardized this for protocols like QUIC, but only described the framework. It does not describe details about how to search for the PMTU. And this is where our work started. And now let's look at how we can use the PMTU discovery framework in QUIC. The PMTU framework uses an PMTU estimation and begins with a small value for this estimation and then sends special packets to probe the network paths. Such a probe packet looks like this in QUIC. It starts with an IP and UDP header, of course, followed by a quick short packet header, and followed by a ping frame, which makes the egg, the quick packet egg eliciting, and then followed by a number of pad frames to control the size of the probe packets. If we get an acknowledgement for a probe packet, we know the network path supports this size, and we can increase our PMTU estimation to this probe packet size. We get an acknowledgement after approximately 1 RTT, maybe a little later if the receiver delays the acknowledgement. If, on the other hand, QUIC's loss detection detects the loss of a probe packet, we resend the probe packet to be robust against loss due to other reasons. But we consider a probe as failed after max probes lost probe packets. The max probes is a constant from the PMTU framework, which is by default 3. We can utilize packet-to-big messages. If we get a packet-to-big message on a probe packet, we consider the probe as failed immediately. Okay, now let's look how we can use the probes to find the PMTU. At first, we should know what are our PMTU candidates. The lower bound of the candidates is 1280 byte because the specification for QUIC assumes that each path supports this size. So we suggest that this size should be used for the QUIC's path validation during connection migration or connection setup. The upper bound is more variable. We can use the minimum of the maximum IP packet size, which is around 64 kilobytes. The MTU is specified for the local network interface, which is for Ethernet interface often 1500 bytes. The MTU will learn from another network device, for example, a router, and the maximum receive unit declared by the remote endpoint. For QUIC, the remote endpoint can set the max UDP payload size in the transport parameter. If we know our bounds, we can reduce the number of candidates when accepting a lower precision. For example, as described in our paper, we choose to consider only multiples of 4 as possible candidates. Next, we specified the order of candidates to probe. For this, we consider 7 different candidate sequences. The first candidate sequence is the upward sequence that uses a list of candidates in an ascending order and selects one candidate after the other. We start with the second lowest candidate because we expect the lowest candidate have been probed during connection path validation. Then we consider a downward sequence that uses also a list of candidates, but in a descending order. Then we consider an optimistic upward sequence that selects the largest candidate first and then continues as the upward sequence. And we consider a down upward sequence that switches between these two sequences. It starts as a downward sequence, switches to the upward sequence, switches back to the downward sequence, and so on. Then we considered a binary sequence that starts with a middle candidate, and here it makes sense to wait for the result of the probe, and if the probe was successful, we continue with the upper half. If the probe failed, we continue with the lower half. The optimistic binary is a variant of the binary where we again start with the largest candidate and continue afterward as a binary sequence. Last but not least, the jump sequence uses a predefined set of sequences, and the downward sequence, a predefined set of candidates, and the downward sequence to jump over the space of candidates. If, for example, the probe for this candidate succeeds, we use the upward sequence to again jump over the set of remaining candidates. And if, for example, this probe fails, we continue with the next a larger candidate after the last successful candidate. So successful probe candidate. Now we need a search algorithm that decides when to select the next candidate, when to retransmit a probe packet, and when to terminate the search algorithm. A simple algorithm would check one candidate after the other. For example, if we use the downward sequence, we have a simple down algorithm that sends a probe packet for the first candidate, and after detecting its loss, it repeats the probe packet as often as max probes defines, which we expect is 3 in this example. And this continues for the next candidate, and after that we found the PMTU. As this makes detecting a failed probe quite time consuming, we, instead of retransmitting a probe packet, start a probe for a smaller candidate. Again, with the downward sequence, our algorithm starts by probing the first candidate, detecting its loss, and then instead of retransmitting it, we start a probe packet for the smaller candidate, the next smaller candidate. And with this, we find the PMTU earlier, but still haven't made a decision about the upper candidates. And now, after a successful probe, we start retransmitting the smallest outstanding candidate as often as max probes defines. After this, we know that the probe failed, and with this we let all other probes for larger candidate fail as well, so we don't repeat the probe for the upper bound. How did we evaluate our algorithm? We evaluate it in an analytical way by defining 4 metrics and by considering a network endpoint that searches the PMTU and uses candidates between 1280 bytes and 1500 bytes that are multiples of 4. We further assume no packet loss due to another reason than the packet size, and we expect to receive no PTB message. With the PTB message, the search is quite easy and we don't see much of a difference between the algorithms. So we expect to receive no PTB message, and the first metric we defined is the number of probe candidates. This is the number of candidates the algorithm probes until it finds the PMTU and terminates. And with this plot, we see our result. On the x-axis, we see the actual PMTU values, and on the y-axis we see the number of probe candidates. And as we can see by the blue line, the number of probe candidates increases for the upward sequence as the actual PMTU increases and has its top on when the PMTU is the largest candidate, of course. Then the next metric we define is time. This is the time needed until an algorithm finds the PMTU. And as we can see here by the color filled area, we don't have a single result for each PMTU, but a range of possible time values. This is because if our QUIC host sends egg eliciting packets other than the probe packets, it might reduce the time to detect lost probe packet, and it might reduce the time to get an acknowledgement for a probe packet. For example, if we don't send any other egg eliciting packets, we expect the receiver to delay the egg by the max egg delay. And if we send other egg eliciting packets, our probe packet could trigger an immediate egg. So our acknowledge time is as low as 1 RTT. We assume an RTT of 20 milliseconds and a max egg delay of 25 milliseconds. And what we see by the result is that the linear algorithms are good in their specific cases, and that the binary algorithms are have an overall small or short time. The next metric we define is the network load, which is the load that an algorithm produces by sending the probe packets until it finds the PMTU and terminates. Here we assume max probes of 3. And what we can see here is that the binary algorithms have around 10 kilobytes of a network load they produce, and the linear algorithms have, in their worst case, around 80 kilobytes of network load. And last but not least, we have defined the average PMTU estimation, which is the average PMTU estimation during the search before an algorithm finds the PMTU. So what we see here is that the binary algorithms find a rather good estimation before they find the final PMTU, and that the downward algorithm doesn't change its MTU estimation before it finds the final PMTU. As we weighted the estimation by the time each estimation is used, we also see the color filled area and had to assume an RTT and a max egg delay. Okay, to sum up, our top 3 are binary followed by up binary followed by jump. But we prefer the up binary over the binary algorithm because it has the potential to immediately find the PMTU or trigger a PTB message. The jump algorithm depends on the initial set of candidates. If one knows accurate and small set of candidates, it could outperform the binary algorithms. Okay, let me conclude our work. What have we done? We presented a search algorithm for the PMTUD framework. We defined 4 metrics to analyze the algorithm with different candidate sequences. And what I couldn't cover in this presentation, but you will find it, you find it in the paper, is that we implemented the PMTU discovery in QUIC, in our QUIC simulation model, and used the simulation to further evaluate our search algorithm. Thank you.
All right. Thank you for that very clear presentation, a very good introduction to MTU discovery and all the nasty snake pits involved there. We have one question from Lucas in the chat. And he asked, do you have any insight when it is good to start the discovery process? And also, how often do you have to rerun discovery? Or do you even have to rerun discovery?
So when to start? I would say start it when the connection is up. So right after connection setup starts the probing. And how often to rerun? Do you mean because the PMTU might change, or what is the reason to rerun the discovery?
Yeah, I don't have an idea.
Okay.
Oh, yeah, Lucas says it might increase.
Yeah. Okay. So the RFC 8899 specifies a timer for this. I believe it's 600 seconds, which seems to me like a bit large, but yeah, that's all I have. I concentrated on the search, not on the things that come after that.
Okay. I assume that also answers Magnus's question, who asked if you actually tested it on inconsistent links that changed the PMT over time.
Well, I did, but this I couldn't cover this in the paper, and it's yeah.
Okay. Yeah, I think there were some how should I say, there were some reports in the QUIC Slack at some point. I think it was about this. Please correct me if I'm wrong, people who were there, that some deployments saw that they could send relatively large UDP packets at the start of a connection, so at a low throughput. But as soon as the throughput went up, some networks would start to actually drop these too large packets, so that you would have some kind of middle box in the middle that says, you can send too large packets as long as they are, limited in amount. But as soon as you go over, then we start, black holing you.
Okay.
I think that was PMT related. I'm not sure.
All right, that's interesting. Yeah, then you should have a heuristic that the PMTU decreases. You can do this with packet loss. If you have packet loss with big packets and no packet loss with smaller packets, then you can have assume that that's a discovery, that a PMTU estimation is wrong, and you have to rerun the discovery. Yeah, I'm planning to do another work with this, but as I said, I couldn't cover this in this paper.
Of course, sure. One thing I was wondering is, where should I put this? One metric I was thinking of is somehow identifying how much potential data you could have sent until you really find the MTU, if that makes sense. Because if you start too low, you will miss out on some bytes that you could have sent if you would have found the MTU earlier. I suppose that's like a derivative from what you had in the metrics.
I mean, how better becomes your throughput if you do path MTU discovery, or what do you mean?
No, let's say that the MTU is 1,500. You start at 1,300, and it takes you a while to find 1,500. And while you're searching, you are still sending two small packets. So you are missing out on the full 1,500 allowance, basically. And to have what you missed out on, how many too small packets you sent and how much bandwidth you lost on that, to have that as like a metric, to me would feel, how should I say, useful to know. But that's a tangent.
I have to think about it, but you can send. You just have to send more packets, and you can send the same amount of data.
Yeah, but then you start getting limited by the congestion controller based on how that's implemented.
Okay.
Anyway, another question that I had was in the QUIC Slack, there was a lot of discussion about using heuristics instead of an actual search, having like, okay, this is a common set of, let's say, 10 to 20 PMTU values that we often observe in the wild. And first using those, and only then switching to this kind of actual searching algorithm. What do you think about that?
Yeah, that's a good point. So you could use a list of common PMTU values. This list might be quite small, then you're done right away. But this list of common PMTU, or I expect that this list of common PMTU values changes over time. And I tried to write a paper that doesn't lose after 10 years or something.
Sure. It's for me, I was surprised that we don't have that kind of list. That was for me like the surprise that came out of the QUIC dev discussion, is like nobody seemed to know what that kind of list was, or even one at this particular point. Nobody's measuring that, even at the big deployments.
Well, there is work where there did measurements and lists MTUs they found with a percent, and you can use this work to create such a list.
Right. The final question I had is that you're somehow wasting space in the pro packets, right? Because you're just sending padding data, but it's a valid packet. So one thing I would consider interesting is looking at, what if we send, let's say, low priority stream data in the pro packets, like real data, but not the high priority stuff, but let's say you have a very low priority stream, sending it in there. What do you think of that? Do you think that would be worthwhile? Or because some of your algorithms really do send like 20, 30 kilobytes of data, which is non-trivial in some use cases.
That's a good point. The RFC 8899 especially noted that these pro packets shouldn't contain data. But what if we have low priority data we can send? Then I guess it's not a big deal, because we have this multiple streams with QUIC, and we don't have this head of line blocking problem.
Exactly.
Yeah, that's a good point. Yeah,
that's definitely something I would like to see investigated sometime in the future.
Yeah,
not necessarily by you, but
of course we don't always have this low priority data. I guess.
All right. I don't see any more questions in the chat, but still some very interesting discussion. So I was very happy with that. So thank you, Timo.
Thank you.
Looking forward to your follow-up work again. Thanks.